All right, guys. So what we're going to do today is we're going to review. Um, we're going to review the. There was 4 topics that we learned in this chapter of how to apply derivatives after Christmas break. And what we're going to do is we're going to review 3. We're going to review the first 3: linear approximation, related rates. Um, I can't think of the third one. Oh, and L'Hopital's rule. And then on the last one, I'm going to go over the 2 questions that you all had questions about. And so that's how that we'll review the optimization. So this one is linear approximation. It was the first thing we learned in here. And so what I did is I found some notes online that were really good, and we're just going to read them together. And then what you'll do is you'll answer one of the questions of what I'll give you numbers throughout the lesson so you know what the question will be. And then you're going to do an exam. You're going to do one problem. That's all I'm going to ask you to do is one linear approximation problem. So this is in lieu of any test or any kind of review assignment. Okay. So let's read this together. And what I want you to do is listen how I explain it and how they explain it. Now that you had a lesson from me and you did some homework, maybe this will make a little more sense. But the idea behind linear approximation, and sometimes it's also called tangent line approximation or linearization, is that we will zoom in on a point on the graph. And notice that the graph now looks very similar to a line. So if you have a curved graph and we want to know what's happening at a single point, if we zoom super close in on that point, we now have a line and we can deal with lines. We know how to write formulas for lines. Consequently, the equation of the tangent line of a function, so that's capital L of x, that's important to know. When you see capital L of x, it's usually a linearization of a function, f of x at x equals a is written, there you go. And that's the point slope form. Okay? That's the point slope form. And that's what you guys were doing in there. But in all honesty, this is nothing more than the equation of the tangent line we used in our previous lesson. So there it is. There's the point slope form, the y minus y sub 1 that you learned in algebra. There it is. I'm just going to take that minus y sub 1 and add it over. And then I'm just going to make it all functionally based. Simply put, linear approximation uses the fact that every curve will always look like a line if we zoom in small enough. If you zoom in super close, it's going to look like a line. And it's this fantastic fact that enables us to approximate another point on the curve that is close to our zoomed in point. So if we've zoomed in on a point that we can understand, so like let's say it's a whole number, or if we're doing square roots where we can figure out square root of 4, if we can zoom in on a single point and know what's happening there, then maybe we can know what's happening super close to that point, and then thus approximate using a line, thus linear approximation. Now, how to do linear approximation. So when you do this problem coming up, how do you do it? Find the point. Oh, by the way, I want you to take out a piece of paper and write this down so you don't forget it. Okay? Are you ready? I want you to write down 2x cubed. 2x cubed. Okay. I'll tell you what to do with that later on. All right, so how to do linear approximation. Find the point we want to zoom in on. So let's say we were trying to take the square root of 3.9. We're going to find the point we want to zoom in on. Maybe 4, because that's super close to 3.9, and we can take the square root of that. Calculate the slope at that point using derivatives. Sorry about that. Take the derivative. Calculate the slope at that point, 4. Write the equation of the tangent line using the point slope form. Now that you have the slope, you have m. You have, here's the formula. You have m, right? And evaluate our tangent line to estimate another nearby point. Okay? So now you just need a point. You need this x, that x right there, that x sub 1, that's the 4. The y, plug the x to 4 into your function, get your y, and then you just, it's not that hard. Example, a polynomial given an initial value. All right, so let's put everything together and look at an example where we will use the equation of the tangent line to approximate a particular point on a curve. I want you to find the linearization of the function f of x equals 3x squared at the point 1 and use it to approximate 0.9. Okay, step number 1, we want to find the point by substituting into the function. So if we're going to use 1 as our point, let's find the point. Let's find the coordinates. So we're going to plug 1 into our equation, 3x squared. So we can plug 1 in there. So our point is 1, 3. That's our x and our y, 1, 3. We plugged the point into the function. Next step, find the derivative. Well, the derivative of 3x squared is 6x. Step number 3, substitute into the derivative to find the derivative. So we're going to find the slope. If our slope formula is 6x, we're looking at 0.1, right? 0.1. Plug 1 into your derivative. Your slope is 6. So you can literally write your equation. Y minus your y is right there, 3. So y minus 3 equals the slope, which was 6. We just found that from using the derivative. X minus your x value, which was 1. Now that you've written out your equation, plug in 0.9 to your equation to find the value. Your approximation. It's not that hard. Find your point based on what's the easiest to deal with. Find your y like by that. Find your derivative of the equation. Plug in your x that you just used to find your point, to find your y, to get your slope, and then plug it in. That's it. Now, I want to draw your attention to the fact that we merely substituted 0.9 directly into our function. We would arrive at the value of 2.43. Using our new method, we calculated the value to be 2.4. Isn't it amazing to see how accurate the equation of the tangent line is in an approximated curve near to the point of tangency? It is amazing because it's God's creation and he made it that way. Therefore, as long as we say near our given point, our line linear approximation will be very accurate. So make sure you don't stray too far from that point. Now, before I go on, I want you to take the double derivative. I want you to take the second derivative of that, what I told you earlier, as your question to answer to. I'm sorry, as your answer to question 2. The answer to question 2 is the double derivative, the second derivative of what I said earlier. Okay. Now here's an example of a cubed root doing the same thing. Okay. Summary. Isn't it enthralling to know that you just did the same calculations as your calculator? Gosh, you're so talented. So together we will look at the overall process and the idea behind linear approximation. Let's jump in. Now, there is a video tutorial. There's examples. Oh, no, I think you have to pay for a subscription there. However, there are examples here that I didn't go over, the exponential function, the square root, but it's literally the same process. So what I'm going to do is I'm going to put this website on your Delta Math homework assignment so you can go back and look at it if you want. Answer question number 2 based off of the things I said in this video. And then you're going to have a linear approximation problem to do in Delta Math after that before we get to the video on L'Hopital's rule. All right, thanks, guys.